Picture this, a computer chip chilled to a temperature colder than deep space. Now hit it with rapid-fire magnetic pulses and boom, you've cooked up an entirely new form of matter. One that, on paper, really shouldn't exist. Wild, right? Here's the promise. By shaking a quantum material just the right way, researchers aren't only adding energy, they're rewriting the rulebook those particles play by. In today's episode, we'll unpack how that trick works, why the early data has hardware designers buzzing, and what it might mean for the gadgets on your desk 10 years from now. First, let's zoom in on the lab bench. A tiny chip sits inside a fridge, hovering near absolute zero. Micro-patterned coils wrapped around the chip fire magnetic pulses at 10 to 100 gigahertz. That's fast, really fast. Fast enough to make electrons and spins reorder themselves in ways nature never intended. The result is a brand new landscape of energy levels called Floquet gaps. Think of them as speed bumps, about 12 millielectron volts tall, that keep the system on a well-marked highway and block out most of the random potholes, thermal and electrical noise, you'd normally hit. Why does that matter? Because less noise means fewer errors. In a prototype spin-qubit array, the error rate plummeted from 3.2% down to just 0.4%. For quantum engineers, that's like swapping a rickety wooden bridge for a concrete freeway. Now let me show you the real superpower. Timing. Instead of only deciding what magnetic field to apply, the team programs exactly when to turn that field on and off. Picture a pulse pattern that repeats every 50 picoseconds for a 20 nanosecond burst. Flip a switch in the control software, and the very same physical chip suddenly behaves like a totally different material. And it's not simply on or off. As the drive frequency is tuned, the chip marches through several sharply distinct phases. Around one sweet spot setting, spins lock into an orderly pattern that survives more than 10,000 drive cycles. Nudge the frequency by a measly 3%, and that order collapses. It's a dial-a-phase control, accurate to better than a gigahertz. Because you're reshaping the energy spectrum, you're also changing which errors are even allowed. Under normal conditions, stray fluctuations can flip a qubit in nanoseconds. Turn on the carefully chosen drive, and many of those flips become energetically impossible, or require a complicated multi-step dance that's astronomically unlikely. That's why we saw almost an order of magnitude drop in errors. Whole channels of noise weren't just muffled, they were switched completely off. Okay, that's the time story. What about space? Those same patterned coils can focus on areas only a few micrometers wide, about the width of 50 to 100 qubits lined up shoulder to shoulder. So one block of a chip can enjoy heavy-duty protection, while its next-door neighbor stays in a normal, easy-to-read state. Scale that up, and you can imagine a 1-centimeter processor tiled into thousands of zones, each toggled in under a nanosecond. And we're not limited to spin qubits. The very same periodic trick works on superconducting circuits, Moiré graphene, even atom-thin semiconductors. Engineers could program electrical transport in time. Currents that flow only at the second harmonic of a drive, edge channels that pop on above a threshold frequency, or insulating bubbles that appear and vanish inside what used to be a conductor. Think of it as a field-programmable gate array, but for quantum phases.
To make that concrete, imagine a test chip, a 5x5 grid of micrometer-scale zones. Some zones get an 18 GHz pattern for delicate logic, others a 72 GHz burst for fast routing, and a few stay undriven for plain old measurement. During a single 30 nanosecond operation, the controller steps through 3 distinct temporal configurations, giving the same slab of silicon 3 entirely different wiring diagrams in rapid succession. You could park a 64-qubit register in a calm, protected phase for 20 nanoseconds, shuttle results through a speed-optimized but less protected channel for 5 nanoseconds, and wrap up with 5 nanoseconds of classical readout. On larger wafers, thousands of these timed islands could run their own sub-microsecond scripts. Sounds great, but there are engineering hurdles. You'll need control stacks that handle thousands of drive channels with sub-nanosecond skew. Today that points toward cryo-CMOS chips sitting just 2 or 3 millimeters from the action, keeping timing jitter under 5 picoseconds. Power is tight too. A wafer hosting 10,000 drive zones, each burning 50 nanowatts, already dumps half a watt into a 4 Kelvin stage, dangerously close to what modern dilution refrigerators can extract. Every wire, filter, and package element will have to pull its own weight. So, where do you come in? Treat these driven phases as design targets, not exotic toys. Start by simulating 100 to 1000 qubit tiles under realistic 1 to 5 Kelvin conditions. Map out pulse schedules that push logical error rates below 10 to the minus 4. Then tape out a 10 mm test die that marries classical routing, shielding, and timing into one tightly co-designed stack. Let that sink in for a second. Because if it works, we get quantum hardware that can literally change its own laws of physics on the fly. So here's what we covered today. 1. Physicists are cooling chips to near-space temperatures and shaking them at 10 to 100 gigahertz to carve out Floquet gaps, energy speed bumps that block noise. 2. By treating time like an extra control knob, they cut qubit error rates from 3.2% to 0.4% and created dial-a-phase functionality with sub-gigahertz precision. 3. Spatially targeted coils let different zones of the same chip live in totally different quantum worlds, protected, fast, or measurement-ready, all within a single 30-nanosecond operation. 4. The same playbook could reprogram superconductors, graphene, and more, opening the door to chips that rewrite their own circuitry in real time. 5. Yes, there are power and control challenges, but smart co-design and cryo-CMOS electronics are already closing that gap. With that toolkit, you're not just building devices, you're choreographing brand new dances of matter. And that means you, whether you're a physicist, an engineer, or just a curious mind, can start asking a whole new set of questions. What phase do I need right now, and how fast can I switch it on? Want to dig deeper? Here are 3 bite-sized steps. 1. Hop onto YouTube and search Topological Phases of Matter, MIT OCW. Watch the first 10 minutes and sketch how time-engineered states differ from everyday solids, liquids, and gases. 2. Find the original research article. Try Exotic New Forms of Matter Shouldn't Exist, Nature article. Read the abstract and conclusion, jot every unfamiliar term, then hit the Oxford Dictionary of Physics to decode them. 3. Download the free PDF of The Physics of Quantum Mechanics by Binney and Skinner and explore the chapter on many body systems. Compare those concepts to today's experiment, whether that's ultra-cold atoms in optical lattices or superconducting qubits. That's it for now. Keep your curiosity switched on, and remember, sometimes the fastest way to invent the future is to shake the present, literally. Catch you next time.